Hey guys, in this video, I will go through lesson 6.7 and 6.8. 6.7 is called Do You Like Green Skittles? So in 2013, Skittles changed the flavor of green from lime to sour apple. Miss Vo takes a small handful of 5 Skittles from a bin of 10,000 Skittles and gets all green. If 20% of the Skittles are green, what is the probability of this happening? The first thing we are going to do is to see if this is a binomial setting, and we are going to try to explain that. So the first thing that we have to make sure we meet is B, which if it's binary in terms of success and failure, that's just picking a green or not picking a green. So we know that B works out nicely. In terms of I, is it independent? So if I pick one Skittle, does it affect how I pick the other? Yes, it does, because then I will have one less Skittle or 5 less Skittles. And then if I n are the fixed number of trials, and here my fixed number of trials is 5, and just seeing how many I get within that 5. Lastly is my S, which is the same probability. So I have 20% are green, so I know that the probability of success will remain 20%. Here, an explanation that you want to put is that it's not independent because we are sampling without replacing our Skittles, like we literally just took them out. Part 2 is to find the probability of getting 5 green Skittles if this is not a binomial setting. So if it's not a binomial setting, which we had indicated in this whole idea of independent. Part 3 is find the probability of getting 5 green Skittles if it were a binomial setting. Think about the binomial formula here. In a sense, use the binomial formula and show your work. In part 4, we're going to compare our two answers from part 2 and part 3 and then see what happens. I'm going to allow you guys to do this, and then you guys are going to see the answer in a second. All right, so here are the answers for part 2 and part 3. So notice that as I do part 1, if it's a binomial setting, notice that denominator had dropped by 1 every single time I select a green Skittle. And also the value at the top, this 2000, was 20% of 10,000. So that's how we get 2,000 total greens. And then it just also drops by 1 every single time. So if I were to multiply each of these fractions out, we get 0.00319. In terms of part 3, we're looking for the probability that we select all of those Skittles to be green. So it should be x equals 5, which is represented by 5 choose 5, and then times 0.20 to the 5th power, because we want all 5 of them green, and then we don't want any that is not green. So that the chance of that is 0.8, and then when we calculate those value out, we get 0.00320. And then as we take a look, so part 4 says to compare these two values. So the values we are looking at is or are these two values here. And notice that as we look at those two values, there's hardly a difference between these two values, even though one is binomial and one isn't. And that reason being is that because our sample size is so small relative to what our population is, it kind of doesn't matter in this sense. So what I'm going to write here is, so it says almost the same. The probabilities in number 2 change so little because the sample size is small relative to the population. This is also called the 10% condition. And what the 10% condition is saying is that when the sample size is smaller or equal to 10% of our population size, replacement and non-replacement is almost exactly the same. If the sample size was a lot larger, then you will see a huge difference between these two values. It's going to help us move on to our second part, where it says Ms. Vo now grabs a handful of 100 Skittles from the large bin of 10,000 Skittles. X equal the number of Skittles in a handful of 100 Skittles. X can be considered a binomial random variable because the 10% condition is satisfied. So notice that if we did 10% of 10,000, we still get less than our sample size. So that means that we can use binomial formulas for this in order to help us solve any probability problems that this problem has to deal with. So part 5 says, what is the probability of getting at most 11 green Skittles. Show your work. So this is what I'm going to do here. So the probability that X is at most, so that means less than or equal to, 11. And then you're going to use binomial CDF, and then the values that we are going to put in here. So we have 100 trials. Our probability remains the same, which is 0.2 from above. And then now we're looking for at most 11. So that is going to show me everything that is less than 11. And then you guys are going to calculate that. The value here is going to be 0.0126. Okay, so part 6 is what is the approximate shape of the distribution? One is easy. So as you can see here, approximately normal or approximately symmetric. It says calculate the mean and standard deviation of X. So this, because it's a binomial distribution as well as being normal, so they can kind of go hand in hand. The way that you can calculate your mean, if you guys remember, is to use the formula mu sub X is equal to N times P. And then the standard deviation of X is equal to the square root of N times P times 1 minus P. So I'm going to plug in some values and then get some answers out, but you guys also try this out for me as well. All right, so these are the values that I have gotten for today. As you notice, if you take a look at the distribution itself, like notice how it turns into 20. Perfect. And then the standard deviation, so it varies about 4 green Skittles from the mean of 20. So part 8 says to redo the problem number 5 using a normal distribution. So now instead of calculating using binomial CDF, how do you calculate using z-scores? So that's basically what it's asking. So as a reminder, to use z-score, the z-score formula in general is the X value that we're looking at minus the mean all over the standard deviation. So we can definitely use the normal distribution now because we have a mean and we have a standard deviation, which you notice we calculate from above. So if I were to plug in some values, 11 would be my X value because I'm looking for at most 11 greens. So it's referring to part 5. And then minus the mean, which we found out was 20 over the standard deviation of 4. So if you look at the z-score, our z-score here is negative 2.25. And then from here, again, this is not the probability because we're going to have to go into table A and see what table A says to determine our probability. So I'm just going to find table A in here. Looking at negative 2.25. So I'm going to zoom in. 2.2, 1, 2, 3, 4, 5. So this is the value I have here. I have 0.0125. Oh no, that is 4. Sorry. We're going over one more. 0.0122. And then, so tables A is saying the probability that X is less than or equal to 11 is equal to 0.0122. So if you take a look at the probability that we found prior when using the binomial CDF is very similar to using our z-score formula. So that's how we know that it's okay to use the binomial formula in a problem like this, even though it is normal, okay? So that was this lesson for today. And then in terms of our lesson target, I will write those in a second. All right, so our important ideas is first the 10% condition, which is when taking a random sample, especially without replacement of size n from a population of size capital N, we can use a binomial distribution if n is less than or equal to 10% of the population. So that our population ideally should be small to be able to do our binomial distribution. However, sometimes binomial distributions is not going to be as accurate as a normal distribution. So when you can use a normal distribution, you're better off using the normal distribution, especially if our sample size is really large. So this is called the large counts condition. And it says use a normal distribution to model a binomial distribution if n times p is greater than or equal to 10 and n times 1 minus p is greater than equal to 10. So these are two conditions that we should make sure it meets so that the normal distribution works for something huge in a binomial distribution. So let me just show you what that kind of looks like. So here's kind of a simulation where it says normal to binomial. So look at the number of trials to be n and then the probability to be 0.2. So if I were to kind of look at my trials, so look at 18 and 0.02. If I were to technically multiply that, that value is going to be small, which is going to be less than 10. And look at my shape. So my shape technically doesn't look too normal. However, if I continue on and start changing these probabilities, notice as the probabilities increase, and my child's increase, look how normal my shape looks. And the perfect one here is actually around 50%, where I see it's like super, super normal. Okay, so that's kind of the explanation of that. So that was lesson 6.7. And then I am going to move over to lesson 6.8. So lesson 6.8 is called How Many Bottle Flips to Go Viral? Scene. The senior talent show is scheduled to take place this afternoon. Michael Senator is in stats class practicing his act, bottle flipping. He tells his friends that the probability of successfully landing the water bottle right side up is 20%. Assume that each water bottle flip is independent, and then you're going to answer some questions. So you guys are going to answer questions 1 through 4, and then I'm going to show you guys the answer real quick. So just try those out before you see the answers. All right, so here are some answers 1 through 4. So the first one is how many do you expect to land right side up? So when you expect to land something, that's like expected value, which is the mean. And we know these all 4 of these questions are binomial distribution because you should have checked already using bins. If you don't check bins, then you technically can't use binomial PDF, CDF. So to find the mean for a binomial distribution is n times p, which again is the same as finding expected value. So it's 10 times 0.2, which is 2. Part 2 is what's the probability he can make exactly 2. And then notice how I labeled NPK. It's helpful to do that, and it's crucial to do that somewhere where you labeled an N and a P. So I'm just doing it on top to make sure my readers know what values I'm plugging into the calculator. And then next is making less than 2. So if he makes less than 2, he can make it 0 times, he can make it 1 time. So notice I use binomial CDF, and then my K value is K minus 1 because I don't want 2. The only ones I want up to is just 0 and 1. So this is 1 instead. Versus problem 4 is the last number is 2 because he makes at most 2. So which I include 2 in this one. So hopefully those percentages were correct on your end. Okay, so next is after the first 10 flips, Michael wants to do 10 more, but his teacher is getting annoyed, which usually does happen, with all the noise and tells him he must stop flipping once the bottle lands right side up. Okay, so this is not like, okay, I'm going to do X amount of trials now. I'm going to do it until I can at least get 1. So this is this whole idea of until. When we have until is the idea of not a binomial distribution, but a geometric distribution. Okay, so it says first find the probability that he lands it on the first try. And then the next one is find the probability that he fails on the first try, but lands it on the second try. So generally, if he lands on the first try, he has a 0.2 probability. If he fails the first one, which is 0.8, lands the second one, 0.2. And then for 7 and 8, you guys try that and see if you guys can get the same values. So first one is 0.2, which I'm going to plug into here. This is 0.16. I'm going to plug into here and so on and so forth. So you guys try those rest. All right, so here are the values that you should have gotten for your table. So the ones that you should have put is 0.128, and then 0.1024, 0.0819, and 0.0655. So part 9 says find the probability that he lands it on the 10th try. Generic rule for finding the probability that he lands the bottle on the kth flip. So yes, we can continue on and then just start multiplying everything together, but it might be a better idea if we just come up with a formula, okay? Okay, so on the first try, notice his probability. We're basically not multiplying any failures on his first try. On his second try, we have one failure and one success. Notice a total of 2. And then on his third try, notice that he has a probability of, he has the chance of failing twice and then succeeding once, so giving us a total of 3. And on our fourth try, he failed 3 times, but made it 1 time. So this should help you a lot in a sense of how to calculate part 9. So you guys attempt calculating that and also write a rule. I will show you the rule and calculations in a second. All right, so here's what I got as the rule. So the probability that x equals k equals 1 minus p to the k minus 1 power times p. So if I were to put values into here, which would probably make more sense, is if I want to flip until I land my first bottle on the 10th try, then I would do 1 minus 0.2. So my probability of failure is 0.8. And that should be to the 9th power. So notice that on our fourth try, we decrease by 1 to get us 3. And then the other extra 1, which should be our success, gives us a total of our fourth flip, versus this one is like we failed 9 times and we achieved the very last time, giving us a total of 10 flips. So that should make a lot more sense. And my final value here should be 0.0268. All right, so part 10 says how many flips do you expect it to take for the bottle to land right side up and why? So think about this question and then we will move on. All right, so in this problem, we are actually looking for the mean here because this is saying, what do we expect? So we're actually looking for the mean. And what we have to think about is what our probability of success is in general. So our probability of success is actually 20%. And to calculate the mean using this 20%, which is crucial. So if I were to convert this, the probability of success is actually 1/5. And to find the mean of a geometric distribution, this is how you would calculate it. So mu sub x is actually 1 over p. And then if I were to plug in a 5th in here, and if you did keep change flip, that would be 5. All right, so you expect to land 1 in 5 tries. And then that goes for, if this was 6, then it would be 1 in 6, so on and so forth. So these are the information that you will need from here. And then remember the formula is 1 divided by p. Okay, so lastly is the important ideas, which I will write out. And then that is the end of this lesson. Okay, so here's our important ideas. The first one is geometric setting, which requires bins as well. So similar to a binomial distribution. And then something else you guys should know is that in a geometric setting, it is skewed right. And then here's our geometric formulas with the mean and the standard deviation. So the standard deviation is new here, which is the square root of the probability of failure over the probability of success. For the check your understandings, you guys don't have to do it yet, but I will assign that for next week so that that will be due next week. So hopefully this all made sense. Email me if you have any questions.